theory is concerned with, okay, here's my encoder, here's my code, here's my decoder. And information theory is interested in, first of all, what's this table that I'm encoding? What are the set of rules? Now, in your computer, there's another set of rules. It's called ASCII. Okay, this is like the most basic computer code there is. And ASCII says 1000001 is capital A. Okay, 1000010, that's capital B. Okay, and so you push a button on your keyboard, you press capital A, and this goes through the wire and it goes to your computer, and then you see a letter A on your screen, and you've just encoded A. The code has traveled through the wire and it's been decoded on your screen. It's an encoding decoding process, just like DNA. Okay? This is what communication is. And so first of all, in any communication system, there is a table. And by the way, the table is almost always implicit, not explicit. If we open our keyboard, we're not going to find this table like written down, but it's embedded.
It's in there somewhere.
It's embedded in the logic
right.
of the chips that are in there. Okay, it's embedded and it's implicit. And somebody who's never seen a computer keyboard, if they had an idea about cryptography or something, they could figure out, oh, when I push this button, I get this string of ones and zeros. When I push this button, I get this string of ones and zeros. And that's exactly how they cracked the genetic code. They just started studying, and so you infer what that is. So communication theory is interested in what is this table, and it's interested in what happens when I send a message through this channel, and what happens when there's noise in the channel. Okay, because everybody who's ever tried to communicate with an electronic device or even person to person deals with, oh, I'm watching TV and the station's lousy and there's snow on the screen, or I'm driving my car in downtown Chicago and I'm getting interference. And so communication theory is interested in how do I get the signal from here to here in the presence of noise and still get the signal that I want. Okay? And so
that's going to play into DNA somehow.
Yes, it is. It's going to become a very important topic when we talk about DNA. And so DNA it's an identical process to computer codes. And it's very interesting that, you know, computer ideas about computers developed early in the 20th century, and, you know, Claude Shannon comes along in 1948. And DNA is discovered in 1953, and when we start unraveling DNA, we find out that this incredibly sophisticated communication system has been around for 3 billion years.
And we just discovered the communication theory that explains it.
That's right. Okay, and so there needs to be no question that communication theory applies to biology. Okay. All of these concepts can be applied to DNA.
Is that debated anywhere?
Only among people who are ignorant, frankly.
Okay.
Okay. People in the know do not debate this fact.
But not in this credible scientific community. This is well understood.
There is no credible scientific argument to try to say that applying communication theory to biology is somehow inappropriate. Yeah. There's hundreds of scientific papers that go very deep into the subject, and so no, there's. Yeah.
You're not claiming anything here that's not widely accepted by scientists.
No.
Okay.
And people have been talking about this for 40 years.
Gotcha.
Okay. So where do we go with this? Well, communication theory is a very sophisticated industry. It's a very sophisticated branch of science now. I mean, everything that gets the ones and zeros from Google to your computer I mean, there are layers and layers and layers of fabulously sophisticated mechanisms that quietly operate to make sure that that message gets to your computer and it's not corrupted. And when you type in A, you know, the A shows up on the other end. And most people never think about this and take it for granted, but it's all there.